Hello, everyone. We are the Polygon team members that will be here at ZK Hack Lisbon. Well, my name is Hector. He's Roger, and the last one is Jesus. And in our daily basis, I would say we are like prover engineers more or less. But today we're here just to introduce you our workshop. Do we have the clicker? Yeah, okay. Well, let's start with just a brief introduction of what we are and what we do. And I normally like to introduce Polygon zkEVM as a very simplified version is that we are a layer 2 ZK rollup. Okay, so here we have like 3 different words that everybody has to understand to be able to understand us. The first one being what is a layer 2. And very simply, a layer 2 is, I like to say that it's like it's something that you build in top of a layer 1 that is connected in some way to a layer 1. And in particular, for example, you can inherit some properties of the layer 1 network, like for example, the security of a layer 1, like Ethereum. But in particular, in our case, we can see ourselves on another chain, okay, on top of the Ethereum chain that does whatever it wants, okay. But whenever we do transact from one state to another state, we have an assurance in Ethereum that what we are doing is consistent and correct with Ethereum. Okay. In particular, I like to say that we are like an EVM inside an EVM. Okay. But our EVM is tailor-made to support ZK-related applications. Okay. The second word is a rollup. And well, a rollup is very simple. It simply means that instead of sending all the transactions that we receive, instead of being sent to Ethereum directly, we roll them up into a single transaction, and the single transaction is the one that we include in layer 1. Okay? So we are paying for a huge number of transactions, the same that a normal user will pay for a single transaction. Okay? That's what rollup is. And the third one is zero knowledge. Okay? The zero knowledge part comes from the fact that apart from sending the transactions, for sure we cannot believe that the transactions has been executed correctly. Okay, so apart from that, we generate a proof of the correct execution of this transaction. Then we send this proof on chain, and we verify this proof on chain. Okay. With that, if the proof is checked to be valid, that means that all the transactions that has been proven are also correct. Okay. Okay, in particular, to be slightly more precise, we do not send one proof per batch. Okay, we do not send one proof per group of transactions. We do something slightly more harder. Okay, so as you can see in this very funny diagram, we have on the bottom layer some amount of batches. Batches are just a group of transactions. Okay, we generate a proof per each of them. And instead of sending each of these proofs to the blockchain, we just run another prover on top of these proofs, just to aggregate them, okay? And not putting a single proof, in the sense that if you verify this proof, then that will mean that all the bottom proofs are correct, okay? And on top of that, we generate another proof, checking that all the groups of all the batches are correct, okay? In the same sense, if you verify this proof, then all the bottom are verified to be proven, and so on and so forth until the bottom one. Okay, and finally, we are just sending one proof per all the batches in the bottom layer. Okay, so we generate as many as we want. And just to let you know a little bit of the benchmark, because intuitively this has to be a lot of expensive, but it's not. Okay, so as you can see here, we just take around 2 minutes to generate a proof. Okay, use a batch proof. Then we take like 10 seconds to aggregate all these proofs. Okay, so just to concatenate all the proofs. And finally, to generate the last proof, just a couple of minutes more. Okay, so in total, like less than 5 minutes to generate all this proof. Okay, and regarding the cost, we are just paying almost nothing just to be able to not only sending the transactions, but proving the transactions. Like the number of transactions are 500. Okay, this is the number for 500 transactions. Okay. Okay, I don't want to stop here too much because this is like the real architecture that we have in our system. Okay, it's not only about the prover, the proving part, the smart contracts, and so on, but we have like a complete overflow starting from when the user sends the transactions to us until it ends up being proven. Okay, in a batch, these batches get aggregated, and finally we just interact with the smart contracts on layer 1 by sending these transactions and the proof. Okay, but we have here like the pool database, which is basically the place where we store all the transactions. We have the sequencer, which is the entity that decides in which order we're going to prove the transactions. We also have databases in which we store our state transitions. We have the executor, which is the one which is in charge of executing all the transactions. And finally, we have the proving part, which is the part that is more interesting to us in this event. Okay, so in the last presentation, it was presented the Circom DSL that we typically use in our stack, but in fact, we have more DSLs that we encourage you to use if you would like to use something different from Circom. Okay, and in particular, our architecture or the way we interpret the transactions and are able to prove them is by having something that we like to call, in fact, it's very similar to like a machine processor. Okay, it's totally structured like a processor. Okay, meaning that we, for example, have a RAM, we have a room, we have a module for checking that the storage instructions are being executed correctly. We also have an arithmetic, a place where we do binary operations, hashing, and so on. Okay, and to implement all of that, we have used 2 additional DSLs. One being PIL, and the other one being ZK assembly. Okay, in our bounties, we will be focused in using the Circom in order to prove, well, in particular, we are very interested in proving the monolith hash function, but we also encourage you to take a look at these languages and see which ones you prefer to use, either Circom or using PIL and ZK assembly. Okay, so you want to do it? Okay. So let's jump now to the hacking tracks.
Like this. Hi everyone. So basically we will have 2 tracks. At the end we'll have like 6K to share between the tracks. The idea a little bit is like you just put these 2 challenges, like usually will be like 3K and 3K. But the idea a little bit is like to check the projects that comes out and share the proper amount to each project. So basically, one track will be like using Circom, make the monolith hash, as Hector just said. And the other one is like using, basically, as Hector just explains, for building the Polygon zkEVM, we build a couple DSLs, and we also use Circom. So basically use whatever stack of the zkEVM that we use on Polygon zkEVM to build another dApp and deploy whatever you want. Can be a game, can be whatever you want. Like it can prove a hash, whatever. And we also like encourage you to check this out. The voltage distribution, I understand. Well, I think well, the idea, as I said, like it will be like 6K total, 3K, but well, the idea is like see the acceptance that every project have and share the amount of money, like share a little bit between the projects that came out.
Okay, so the first track, even if it looks like very specific, there is a very good reason in why we want to build the monolith. Okay, and the main reason is because right now, underlying all the zkEVM, we are using Poseidon, like for everything, except for where you have to use SHA-256. we decided to use Poseidon because at that time, Poseidon was the one that was easier to express using an arithmetic circuit, okay, meaning that proving the correct execution of Poseidon inputs and outputs is very easy compared to other alternatives. Okay, so in particular, we are interested in Monolith because it looks like a very good replacement to Monolith because it not only improves in the proving side, okay, it's not only easier to express in a circuit and therefore being able to generate proofs on that, but it's easier to compute Monolith inputs and outputs, okay? So, well, basically the objective is implement the Monolith hash function in Circom. But as I said before, if you take a look at PIL or you already know PIL and you're excited about this language, you can do it as well in PIL, okay? PLA and Circom are very distinct in how you express constraints. And in some parts of Monolith, it will be easier in Circom and in other parts will be easier in PIL. Okay, and for the criteria, for sure, we expect you to make a correct implementation. But overall, we expect that implementation from one side is sound, okay, meaning that you do not miss any important constraint. And on the other side, we expect it to be as succinct as possible, okay, meaning that you do not add more constraints that are strictly necessary in order to verify a Monolith implementation, okay? And just as like a bonus thing that we will very consider is, for example, if you're using Circom, it will be awesome, and in fact, it will be easy for you if you decide to use Circom to use like very recent features of Circom, like anonymous components or tags. Okay, so I'm going to go fast through this. But basically, as you can see in the table, if you take a look at Monolith and try to compare Monolith, for example, against Poseidon and Poseidon 2, which were the past candidates to do the very same thing, in terms of how many time do you need to compute Monolith inputs and outputs, it's almost 10 times faster than the previous candidates, okay? And if you compare Monolith with very well-known and very widely used hash functions like SAS256, their timings are very, very, very tight, okay? So that means that this hash function is really, really fast. Okay, and just as a crash slide on Monolith, this is what you will need to be able to implement in Circom, okay? Nothing has done that, okay? Monolith is just a recursion of more rounds than what you see here. And for example, the second part and the third part, the bricks and the concrete part, I would say, are very straightforward in Circom. And the most challenging part is the first one, because the authors recommend to use what we know as a lookup argument to be able to implement this part, but you can do it anyways using arithmetic operations. Okay, this is the part where it's more like invention is up to you. Okay, and for example, this is from the actual paper of Monolith. These are the expected numbers that you are supposed to be able to obtain. For example, they got these numbers using the Plonky 2 system. And as you can see, if you compare Monolith and Poseidon, the proving time and the verification time is double better from the former to the second one.
Hi again. So the zkEVM track, as I say before, like it will be like using the zkEVM stack, which basically it's Circom, PIL, or ZK assembly. Whatever version of these three, it will be okay to do it. Well, the idea will be like make a dApp if it's complementary with smart contracts better. So for sure, this will be a bonus. And a little bit we will measure like the how secure is your dApp, how if it makes sense and stuff. And of course, if you end up having an end-to-end flow, it will be much better. And well, we encourage, well, the code must be open source for sure. And well, if it, in case of the smart contracts, you can deploy it in whatever testnet. Just well, share us the link and that's it. And if you have any questions about whatever this tooling is, we are at the booth and you can come for sure. And now we'll do a live tutorial.
So in order to help you, and because I don't know if you're familiar with Circom or not, but even if you're familiar, sometimes it might be overwhelming if you have not done a Circom project in a while to just get all the tools back together and do all the setup part, and get all the commands and go through the documentation again. So what we've tried to do, we'll send this link later in Discord, I think it was. Yeah. And Telegram maybe. So we have tried to create an example repo, which will provide the link and basically has like several examples and has a lot of a few scripts that you can use just to get started easily instead of trying to go from scratch and try to search for our documentation. So here in this repo, what you will see, let me check, let me organize. One second, let me close things. And so basically here, I need to change the layout, whatever. But here you can see the repo. In the repo, what you will find basically is like a few, probably not the best documentation, but still enough to get started. And here you can, we will also provide many links about Snark.js, Circom, and also some links to our repos and documentation about PIL and zkEVM, because even though it was not originally the main idea we had, you are, as Hector and Jesus said, you are always encouraged to use PIL or zkEVM. And if you want to go that way, we are happy to help you. And if you have any questions, you can reach us and we can discuss together. We can try to help you understand how everything works, how to connect things, and so. So in this, what you will find in this repo, basically there's like a few examples that they are kind of described here. The first one you will see is a Poseidon one, written in Circom. Basically, this is the exact Poseidon that's on Circom lib, because if you're not familiar with Circom, as I think Thor said, there's a lot of libraries that are already written in Circom, most of them under the repo Circom lib, I think it's called. So basically, we have a Poseidon, which is another hash function that you can use and see how that works. And you will see that, and now I will show you later, that there's two implementations of Circom. Because as Hector said, there's if you want to go for the monolith path, you will face one challenge, that's lookups, which are quite tricky to do in Circom. But you can do what's called custom gates. So, and in this repo, you will see some documentation about custom gates, and you will see how, for example, the whole Poseidon hash was also right. We had a custom gate for the whole Poseidon, which is not the intention for Monolith, but can give you some ideas on how you can use custom gates. And then there's, as we said, we are trying that, of course, for new developers, but if you have been familiar for a while, there's been new features going on that, as Hector said, anonymous components and tags, and also the inspection functionality, which are some features that are what we consider as that good practices. So if you're new, that's perfect, because then you will learn from scratch, and that's even better. But if you have already done Circom circuits before, it's good to introduce this, because as I will show you now, it gives you like more clarity to the code, it improves the security, the readability, which is also good, right? So if I go to the repo and see if I can show you a bit. Where's my mouse? Yeah, here it is. So as I said, the first, you can see here, and there's Circom, there's different circuits. If we, I think the screen is big enough for sure. So you can see here in Poseidon, there's like, as I said, This is a real Poseidon implementation that's used in production in many services. And you can see how it was implemented. And you can also check there's this Poseidon custom. The set it uses custom gates, but it's actually the same. So there's two different ways of implementing Poseidon, both of them different but equivalent, if that makes sense, because at the end the result is the same. And we have, where is this, test Circom, in which you, there's a, I'm assuming that all of you have seen a Circom template before. If not, I will also provide the link for the basic tutorials. Although it's true it's a low-level language, I think it's pretty easy to understand and move forward. And so what I was saying is here is you can see we're just comparing those two versions. And that's the first example. Then we have here in the package.json, come on. Okay. Whatever. Yeah, whatever. I think I'm going to go down like this. So here, as I was saying, even though you have developed Circom circuits before, it's usually annoying because you need to remember what were the exact commands, what you need to write to compile, to generate a proof, to verify the proof, depending on the prover you want to use. So we've put together a bunch of these scripts. So for example, here you can see compile, which is basically the instruction to compile any circuit. Then you can either generate witness with JavaScript and C++, and this way you don't need to waste time, because it's not a lot of time, but we're in a hackathon, we're time constrained, so it's good for you to have some tools to get started right away. And also, as you can see, we have different Circom. You can generate different types of proof. Right now, we support Flonk, Plonk, and Groth16. Here we have the scripts for Flonk and Groth16. But Plonk is literally the same as Flonk, just changing a few letters. We can update it later. But this way here you have, by just running npm run Flonk, it will generate the whole setup, proof, and verify that proof. And then you can, if you want to use it, you can get this and just use it however you want. And also, that's one way to generate the proofs using scripts. But we also have added a test in which you can, let me see if I can, yeah, here, Flonk test and Groth16 test. That's basically the same, but again, it's just how you would do it in a JavaScript program that you want just to run. And this is probably more useful for the ZK. Well, it's useful for the ZK. If you want to go for a ZK app, here you can see how snark.js is called, because snark.js is another library that Circom has to generate the proofs. And here you can see how you can do the different calls to generate, from generating the setup to generating a proof or verifying it, both with Groth16 and Flonk. And what you will also find in this repo is some examples of good practices. What we're saying, use tag, encourage people to use tags, your anonymous components. So for example, you can see here we picked a random, it's just a template that was in Circom. It's basically, it's not important, the template itself, it's just a multi-and. Basically, you just give in a number of inputs, you just check if all of them are 1 or not. But this was the original template that was written a long time ago, like probably 3 or 4 years ago in the Circom lib. And then we have a second version, which is, as you can see, much more compressed and much more, at first glance, if you check this version, you can much more easily, at least for me, understand what's going on. So you can check if n equals 1, there's one thing, if n equals 2, one thing. And otherwise, you just do a split in 2 and then do a recursion on it. And so that's what you say it's important to use it, because everything will be the same, the proof will be the same, nothing will change, but from the developer perspective and from the and another people that's watching it, I feel it's much more easier to read and understand what's going on here. That's 4 lines, and it's like organized that here that you can just, okay, so here's an AND. What's happening? You're setting each one variables individually, which is kind of annoying. And then also one other thing that's quite interesting to know is the usage of the inspect when compiling. And here I'm going to put an example that, I don't know if you've heard, like it was early this year, there was a post in Medium about $1 million, it was called $1 million ZK bug caught early. Basically it was about a Circom pairing library that JSON did, and allowing BLS signatures, and there was an issue in the circuit. So basically, this is actual real code of that library, and what was happening, and it's obvious but not obvious when you write, because also you can see here, this is all code, so maybe if this was with anonymous components, it would be like 1 line each. Here's like 7 lines and not that clear. But what was happening here, I just don't care about what's going on. They're just verifying some signatures, whatever. But here you can see lines between 103 and 107. It says check all lengths that are basically it was checking that all the numbers were well constrained, were less than a big number. And the problem is here, and that's what one of the things that Hector was mentioning, that it's very important that the thing is sound, is that there's constraints for everything. I think it's better to have extra constraints rather than missing ones. Although, of course, if you can achieve the same with less constraints and be sound, that's perfect. But it's preferable to have more constraints than necessary and maybe checking things twice than rather not checking. And what was happening here, if you see line 106 and you're a bit familiar with Circom, you will see that you are just doing big less than. But you are not, and basically big less than is a template that returns 0 or 1, whatever, and you wanted to check that all numbers were less than, but you were not checking the output. So then you were doing a check, but you were not checking the output, and then there was a huge bug here. And why I'm telling all this, because a few months ago there was a new functionality that was added in Circom, and let me see if I can write. Yeah, I think it's npm run compile. No, not this one. Yeah, this one. And there was a new functionality that when you compile, instead of doing a straightforward compilation, you add -- inspect. It will explore all your circuit and do this automatic check that I'm using all the variables. Is everything constrained? Then the constraints may be wrong. That's another thing. But at least you will not miss constraints. And for example, if I run it, you will see here, it's obviously saying what I was saying, that, okay, so in this template, this output, basically the less than, does not appear in a constraint. And that was originally like a huge finding. Oh, we have like a huge bug, very difficult to find, caught early. Now with Circom, when you just compile it right away, you can detect all those bugs like in a second rather than having to explore the whole code. And maybe if the project is not too big, it's fine, but when you have some projects like Circom pairing that were huge, it's very useful because you will make sure that everything is constrained. And this will be available, as I said, in Discord. I think we will also add, there's already there's 2 folders. One that's called Circom with all these Circom examples. There will be another which is more for the Monolith part. We will also use. We will also add. I think it's already there, but we need to check that everything works fine. zkEVM example, basically how to use to create a zkEVM and maybe use a Circom and then integrate it with a smart contract. So also you have something to start with and to get some inspiration, see how things are connected. And regarding other DSLs that we use, as I said, there's not specific repos like this for you to play, but there's the main ones. And feel free to ask any of us, and we will try to help you, explain how everything works and all of this. And I think that's it.
Yeah, use a couple of nodes just to that you can do these things a little bit much more harder. If you're interested in going through Circom, even if you are new to Circom or you are very experienced, I would recommend you to take a look at the official documentation of Circom because it has recently been updated with the recent features that the owners of the compiler have been adding during these months. And on the other side, if you're more interested in DSLs like PIL, or maybe you just want to build a zero-knowledge application on top of the Polygon stack, I will recommend you to go to the official Polygon documentation, Polygon ZK EVM documentation, because there you will find everything that you will need. Yeah? You will have specifics at how PIL works and how you have to think in order to implement something in PIL. And also you will have how we interconnect all of our stack. If you remember the slide with all components in the zkEVM, you will see the documentation exactly what do we use and how we connect all these components. And well, just to rephrase a little bit, Roger, the inspect command will prevent you, will not always prevent you for doing things wrong. Okay, in some scenarios or in some examples, it will be super useful, like the scenario that Roger has shown, because Circom by itself will be able to detect that you were doing something wrong. But in other scenarios, for example, if you decide to go for Monolith, maybe the compiler will not be able to say you what you exactly are doing wrong, but at least this flag will tell you that there is something that makes no sense for the compiler. Okay, but it will not know, it will not be able to decide what you are doing wrong. Okay, so in some parts it will be super useful. In other parts, like let's say the process of correcting all these mistakes will be a little bit more handy. Okay, and you have the presentation? No. Okay. No, it's okay. It's okay. So yeah, I think that's basically it. So let's hack together. Thank you.
So since we are actually, this is a little earlier than we had scheduled, if there are any questions, we can actually take them now. I don't know if anyone has any specifics. I know this was very detailed. And maybe you don't yet know if you want to hack. Oh, there's a question back there. You got it. Just wait for the mic so we get it on the video.
Yeah, so there's a library called circumspect, and what's the difference between circumspect and the inspect flag in Circom? And maybe...
Can you repeat the question, please?
Yeah, there's I used to use a library called circumspect before the inspect flag was released for Circom, so I would like to know what's the difference between those two.
No, don't know the difference, honestly.
Oh, okay.
But it's just like, I think, I don't know how Circom inspect works. I think inspect is a lot more detailed and provides a lot more, does a more detailed exploration is integrated directly in the compiler itself. So when you compile, it will do all this instead of having to refer to external libraries.
I see. Also, like for the monolith hash, so do you need like the benchmarks to be compliant with what we showed us?
I mean, the numbers that we show were just, I will say, speculative. Yeah. Okay, what we expect are that at least that the number of constraints that you use, let's say to implement the monolith, are at least better than those that you obtain with Poseidon 2, and variants.
Okay, one last question is like for testing, we need also compliant hashes, for example, test cases for the integrity of the hash function that we want to develop.
Yes, exactly.
And you provide that, I assume?
There are libraries where they have implemented the monolith if you need to, yes, okay. For sure. Just ask us and we can provide to you.
Okay, thank you.
Okay, guys, do we have any other questions by any chance? Now is a good time to ask them. Yeah.
Hello. I'm asking about the arithmetic of the two prime number used. I don't see other prime number.
Yeah, so
The
the first,
Mersenne 31 and I think the Goldilocks.
the first one is the Goldilocks one, which is very well known. And the other one is one that is trying to be used, which is called the Mersenne 31 one, which is a 32 bits prime number. It's another one that is also being tried to use as a replacement for Goldilocks. But it's something that is still ongoing research.
It is possible to use other prime number or just these two?
For the implementation, yes. Yes. I mean, the two that were mostly used by the original authors, and in fact, there is a part in the Monolith which is called the MDS matrix multiplication, which in the paper you can find those which are more optimized for these two prime numbers.
Okay. Can I ask about the algorithm of the multiplication and the inversion in the prime number?
Can you say it again? Because
Which algorithm is used for this implementation? For example, Montgomery or which
for the permutation matrix, you mean?
Yes.
Yeah, so this is like in the diagram that I show with three different operations in order to implement the monolith. The MDS multiplication is like the last part of the permutation. So you will need to implement in Circom this matrix multiplication, okay, in order to implement monolith.
Okay. Thank you.
Welcome.
Thanks for the math questions. Yeah, we have another one up there. Thanks, Ali.
So the last time I looked into this code of Circom, I thought it was maintained by the team called ident3, but somehow it's now Polygon. Am I right?
Right now, the guys who are behind the Circom compiler are from university in Spain, from Madrid University, which are in collaboration with ident3. But yes, right now those who are working in Circom are those guys and Polygon team members.
I see. So my question is, just out of curiosity, do you have a plan to add SecP256K1 as a field?
I think that there's many fields that are going to be added in the near future. I think right now you can specify in Circom like the prime you want to use. And you can, I think at least there's BN 128 and Goldilocks. And there's, I think they are finalizing the test with a few extra ones. Like.
So in the close future, you will be able to decide which prime you want to use in Circom. Okay, awesome. Right now we have a small set of prime numbers. In fact, those prime numbers are the ones that we are using in the zkEVM. But we expect that in a near future, you will be able to decide which prime number you want to use in particular.
It's going to be awesome if it's supported out of the box without some crazy gimmicky, extension out of it. Yeah.
I completely agree.
Thanks.
Okay, some quite an announcement here, I guess. ZK Hack. Any other questions from the audience? Yeah, in the back.
Hi. How ZK assembly related to the Circom, or are they related or not? The ZKS is a part of your ZK stack, and you.
So the ZK assembly, which is another DSL, which is very low level. It's the language that we use to interpret the Ethereum opcodes. Okay, so we have.
So you use the ZK assembly for implementing the zkEVM Hermes or something like that?
We use the ZK assembly to not only to interpret the EVM opcodes, okay, but also to prove some part of them. Okay, so zkSM is able to prove some parts of the opcodes that we interpret, but then the rest of the parts, because they are not easy to implement in ZK assembly, we do it in PIL. Okay, so I would say that the interpretation or the proving part of the EVM is done with PIL and ZK assembly. Okay, and then we use Circom in the recursion step of our proving system.
Okay, thanks.
And we use we are able to generate Stark proofs using PIL, which we cannot with Circom.
Okay, thank you. So yeah, do we see any other questions? Yes. Yeah, it's fine. That's what we're here for.
Regarding testing in Circom, so there's the library called Circom tester.
Yeah, and wasn't tested. Yes.
Yes, and I did the benchmarks. It's 10 times faster than Snark.js, Growth 16, for example. And I wonder, do you sacrifice security to have such faster testing framework for that compared to Snark.js, for example? Because once you fetch the signals and the results you want to compare with Circom tester, it's pretty much faster and with the same results.
Circom tester is it's not generating a snark proof. It's just compiling the circuit and then checking that the witness is valid or not. But it's not generating the proof for that witness.
Okay, so it's doing the same calculation as Circom, but not generating a proof.
So when you use Circom tester, you're just compiling the circuit in R1CS, and then you provide a witness, and the program executes that witness and check that all the constraints are satisfied. And when you call Snark.js, you need to specify which kind of proof do you want, either Snark.js or Flonk or Plonk, and you actually generate the proof.
Oh, okay, so the difference is proof generation.
Yes.
I see, thank you.
Just to be a little bit more specific, the Circom tester, what it does is generates let's say the trace or the witness of the circuit. And this in fact is expressed what we call the R1CS constraint system. And the Circom tester, what it simply does, it checks that this witness satisfies the R1CS constraint system that is supposed to satisfy. Okay, and in contrast, Snark.js do much more than that. Okay, in fact, in Snark.js you could have I would call it a pre-setup or pre-process step in which you actually run the Circom tester, just to ensure that the witness that you are computing is actually a valid witness. But then you have the process of generating the proof and verifying it, which is completely different from verifying that the witness satisfies the R1CS. Okay.
Great, thank you guys. Okay. So yeah, just in case you actually come up with more questions, there's going to be a QA tomorrow on the main stage here at 1:30. So yeah, feel free to sleep on it and come back tomorrow with actually more questions.
And just as we said, there's 2 tracks, and even though at the website it was originally saying the boundaries were 5K, 1K, that's not actually true. We're thinking more of a 3-3, and also it will also depend on what you guys, if you want to play with Circom, you can either go for Monolith or go for another kind of project, and depending on the different submissions, we'll decide how we split the boundaries. So don't think, okay, so maybe if you want to do something with Circom, you don't need to be attached to Monolith. You can do whatever you want, and then we'll see depending on the submissions.
Just do something, I guess, is the message. So yeah, thank you very much. We're going to actually have a short break now since the next workshop is in 10 minutes. So yeah, deploying zero knowledge proof on Aleo will come back in 10 minutes. Thanks, guys.